Introduction to Single-Phase AC Circuits for Phase 4. RLC circuits. R for resistive, L for inductive, and C for capacitive. All AC circuits contain these three components, and they are known collectively as Z, or the total impedance in a circuit. Today we will focus on the resistive and inductive parts only, which is the RL circuit, without any capacitors, and learn how to answer questions asked in your exam. RL circuits have both a resistive load and an inductive load. Loads can be considered devices which draw current. The RL circuits can be in series or parallel, both series and parallel. There is no such thing as purely inductive load, so we include resistance also. This is also true of purely resistive circuits. For example, as we learned in Phase 2 or the earlier stages of the apprenticeship, we assumed that all circuits are purely resistive in AC circuits, in order to learn the principles of AC theory. Now we will learn the reality of AC circuits. Not simplified like in Phase 2. We also assume that domestic residences are purely resistive, as there would have been very little inductive or capacitive loads in the past. This is changing, however we still assume this to be the case. Here is an example of a simplified resistive-only circuit in series. Now we can add an inductor into the circuit, represented by a series of squiggly lines that look like a coil of wire. This circuit better represents the reality of an AC electrical circuit. The symbol for an inductor is L and the unit of measurement for an inductor is H, or the Henry. Here is also an example of a RL circuit in parallel. We will look at examples of each of these in the sample questions and answers later. Firstly, what is an inductor? An inductor is simply a coil of wire, also called a choke, which produces a magnetic field when current flows, which pushes back and resists current, and this magnetic field stores energy temporarily. An example of an inductive load would be a motor where copper is wound up in coils. As stated before, more items in our homes now, such as washing machines which have motors, are inductive, yet we still assume that domestic dwellings are still purely resistive for simplicity. This is not the case in commercial or industrial settings, where it is very important to understand these principles. A great help is the acronym CIVIL, or civil. This acronym will make this topic easy. Remember it. C for capacitor, I for current, V for volts, I for current, and L for inductor. Break it down to two components. CIV and VIL. CIV in this case for capacitors, the I comes before the V, so the voltage lags behind the current. More importantly for us now in inductors is VIL. The V comes before the I, and therefore the current lags behind the voltage. Here at the top is a waveform example of a purely resistive circuit. The voltage and current are perfectly in phase with one another, and thus gives us a perfect power factor. Power factor will be explained in a future video. This, however, in reality is impossible. At the bottom is an example of a purely inductive load with no resistance. The current is lagging behind the voltage phase by 90 degrees. This example would also be impossible, but it shows why this would be a bad scenario and cause a lot of power loss. We want the current and voltage to be in phase, or in sync together as close as scientifically possible, though they never can be 100% matched up perfectly. Now we will look at some examples of questions that will be asked in exams for RL series and RL parallel. As in Phase 2, we learned that in parallel circuits, the current is split between loads, drawing on current depending on resistances or impedances. But no voltage drops. In series circuits, we have voltage drops across loads, yet current will stay the same as supply. Let's start with RL parallel circuit. Question 1. Calculate the current across each component. R equals 11 ohms, L equals 0.7 H, and the potential difference, voltage, equals 110 volts at 50 Hz. With the information provided, we always draw out an example to make it easier for ourselves. Using Ohm's law and our triangle, we can calculate the current across the resistor. IR, or current at the resistor, equals voltage over resistance. That is 110 divided by 11. Answer equals 10 amps across the resistor. In order to get the current across the inductor, we need to convert the henries to ohms. To do this, we need to find the inductive reactance, or XL, of the inductor. The formula is as follows. XL equals 2 pi FL, where F is a frequency of 50 Hz and L has an inductance of 0.7 henries. We plug in the numbers provided and get an answer. XL equals 219.9 ohms. Now we can find the current through the inductor using Ohm's law again. IL equals U, divided by XL. IL equals 110, divided by 219.9 equals 0.5 amps. Now we can find the total current, or IT, at the supply of the parallel circuit. IT is equal to the square root of the IR squared plus IL squared. These are the figures we calculated beforehand. This calculation is shown on the screen. I total is equal to 10.01 amps. Let's do another example question of RL parallel. Calculate the supply current, I total. Firstly, again draw out the circuit. This will help you visually. U equals 230 volts at 50 Hz. R equals 50 ohms, and L equals 0.5 henries. As the inductor value is given to us in henries again, we need to find the XL, or inductive reactance, to find the total current. First, we can easily find the current across the resistor using Ohm's law again. IR equals U over R. Plug in the numbers as shown and we get 4.6 amps. As shown in a previous example question, now we find XL using the formula for XL. This gives us an answer of 157.07 ohms. Now we can gather the current across the inductor using XL instead of R in Ohm's law triangle. IL equals U over XL. This gives us a result of 1.46 amps across the choke, or inductor. IT equals the square root of IR squared plus IL squared. With our numbers entered into the formula, we get a result. The total amps in the circuit is 2.4 amps. Sometimes questions can be easier, as shown here. The question will already give you the value for XL, so we do not need to convert the inductive value of the inductor in henries to ohms, using the inductive reactance formula. We simply use Ohm's law to find the two current values across the resistor and inductor separately. Draw out the circuit using the information in the question for better visualization of the circuit. Once we find the current values for IR and IL, then we use our formula for I total as demonstrated here. I total is 2.4 amps. That concludes simplified RL circuits in parallel. Now we will look at questions in RL series circuits which have different voltages across components. To find the total supply current, which is constant throughout the circuit, opposite to parallel circuits. If you remember from phase 2, we need to find the total impedance, or Z, inductor and resistor in circuit. Think of a rock blocking a small river. The rock impedes the flow of the water, and impedance, or Z, is therefore a kind of total resistance in an AC circuit after resistances from resistors, capacitors, and inductors are added together. The formula for impedance in RL series circuit is Z equals the square root of R squared plus XL squared. Question 1. Calculate the value of impedance in the circuit. Impedance, or Z, is also measured in ohms. Draw out the circuit and plug the numbers into the formula as shown, and we discover that Z equals 5 ohms. Question 2. Calculate the current from supply. As we are given the inductor value in henries, we need to convert this to XL using the inductive reactance formula. When we find XL, we can then find the total impedance of the circuit using the formula. Plug the numbers in, and then we have the impedance value of 35.96 ohms. A tip here is to use the Ohm's law triangle and replace R with Z. Then it can be shown that I total equals U over Z. This is 2.78 amps, unchanged in the whole circuit. That is the basics of RL parallel and RL series questions. There are volt drops across loads and series questions to learn, and we will do this in the RC series in another video, as this video is quite long. We will also look at RC parallel examples. The learning list is as follows. RL parallel, RL series, which we covered here as an introduction to single-phase AC circuits. RC parallel, RC series. RLC parallel, RLC series. And RLC parallel and series combined. Also, we will cover phasors to show these results on a graph and eventually our power factors. Cheers, and see you on the next one.